Welcome to the NASA series Exploring the Moon, where we take a behind-the-scenes look at the preparations for humanity's return to the moon.
We are so excited about the Artemis program and the return of humans to the surface of the moon in 50 years.
There are parts of the moon and craters that have not seen the sun in over 1 billion years.
I didn't even have enough light to see the ground in front of me and make sure that I was walking safely.
You've done a spacewalk, you're ready to get back in, you need to clean your suit off. How are we going to do that?
Hi, I'm Stephanie Sipola, and in this episode, we'll be speaking with Dr. Don Barker, a NASA subject matter expert in lunar environment and lunar geology. Thank you for being here today, Don. It's great to have you.
Hi, Stephanie. Great to be here with you.
We are so excited about the Artemis program and the return of humans to the surface of the moon in 50 years. This is really exciting.
Yes.
And this time when we go for the Artemis program, we're going to go to the South Pole. Very different from the Apollo era. But it's not easy.
No.
And so we have you here with us to talk about some of those challenges.
That's true, Stephanie. It's great. And we'd like to look at three of the specific challenges are dust mitigation, surface lighting at the Lunar South Pole, and the thermal conditions at that area also.
Okay, so let's start with your favorite. Let's go straight to dust.
All right. Sounds good.
All right, so the moon is dusty. So is the planet Earth. Why is it different on the moon?
The moon is interesting in the sense that it has an almost unchanged surface for the last three and a half billion years.
Wow, that's sort of mind-blowing. What
Yes,
does that mean
yes.
to explorers?
To explorers, it means that the surface is a very broken up, distributed surface set of surface materials of broken rock, and a large portion of that surface material anywhere. It's called the regolith,
Okay.
and its depth is estimated to be anywhere from 15 feet to 60 feet, depending on where you are on the planet
Okay.
or on the body. And the majority of it is extremely fine materials,
All right.
smaller than beach sand. So it gets.
What about baking flour? Is it that fine?
It is that. It does get to be that fine.
Wow,
A lot
okay.
of particles are below 70 microns, and a human hair is roughly around 100 microns diameter.
Okay.
So we get really small materials there.
Right,
Yes.
right.
Broken up material that has been fractured and distributed over time by every impact, all the craters we see that we can actually see when you see the moon with our naked eye, all the circles and stuff we normally see. Those are the impact basins and craters, and
Okay.
every time one of those events occurs, it just pulverizes and continuously breaks down, melts, distributes these materials.
So then why is the dust on the moon that much different than the Earth? I mean, you talked about the craters.
Yes. But what the Earth has that is extremely unique in this situation is water. Water is the great conveyor belt of all this material. In fact, it's what causes the erosion and breakdown of this material over time. You start in the Rocky Mountains with big chunks of rock, and they slowly break off and fall, angular, fractured, and then water brings them down to sea level eventually. And this process on Earth just keeps going over
And
and
the
over.
water smooths out the surface too,
Yes, it
right?
does. Yes, it does.
Okay.
And so on the moon, we don't have that. We
Right.
don't have that process. We have impacts from meteorites and cometary material that just basically pulverizes with lots of energy. It will melt it sometimes. It will fling it out into tiny little particles that cool and settle all over the planet. You can see the crater rays on some of the, like Tycho crater or something like that, where nice, pretty crater rays extending out.
Right.
And you know, that's pulverized, broken up, smaller material. That's the weathering process on the moon.
Okay.
But time is the great conveyor of all this. It takes a lot of time to break apart and distribute and move this stuff.
Right, right. And so what's missing on the moon as compared to the Earth story you just told is that water and the atmosphere.
Exactly.
And so besides the particles being really small, they're really sharp too, aren't they?
Yeah, like I said, in the erosion process on Earth, if you go to the Piedmonts, the base of mountains, where you get fractures, over like a winter cycle where frozen water fractures off rocks.
Right.
Those rocks are angular and depending on the rock material itself, can be kind of sharp. On the moon, same thing. When it's pulverized and it gets smaller and smaller, and a lot of it's glass, if you melt, a high energy impact will melt the existing material. Tiny little, and one of the cool ones to see, one of the interesting ones to look at is the volcanic glasses from like Apollo 15 or 17. Pretty emerald green or amber orange glasses.
Really?
You can see when one's been hit and chipped. And so you got a nice little sphere with this little conchoidal shell divot out of it, and the edge is just a little bit sharp.
Okay.
So that happens over and over and over again. You'll have broken pieces and they get sharp.
Okay, so what does that mean for our explorers?
That means that dust will get in and on everything that we put in the lunar surface environment.
Okay.
So
but we have gravity.
Yes,
So
we have
will
gravity.
it just fall right off? I mean, can you just do a little dance and dust yourself off?
Unfortunately, no. The environment on the surface of the moon is highly electrostatic, and there are electrostatic forces that allow dust to stick to all the materials. They stick to themselves, they stick to materials, they stick to everything.
Okay.
Now, how well they stick is still something that depends on the material itself.
Right.
So we're in the process of studying that. But it sticks. Bottom line, we were recently at one of our lunar dust test facilities with one of the astronauts, and we'd really like to show you that video.
Great, let's look.
Hi, I'm Dr. Kristen John. I am the Lunar Dust Mitigation Technical Integration Manager for the Space Technology Mission Directorate, and I'm here today with Don Pettit to talk about lunar dust and lunar dust mitigation. So we call it lunar dust. It's also called lunar regolith. It was basically created over the creation of the solar system. Because there's no atmosphere on the moon, you basically have the bombardment of micrometeorites that created this fine surface material that we call regolith or lunar dust.
Okay.
And there's different types of simulants. So what we're touching here is not actually lunar dust. This is lunar simulant. And so we have teams of people and companies that have created different simulants to mimic the properties of the lunar dust. This one in particular mimics the lunar highlands. There's other material that mimics the lunar mare. And then we use this for the most part to study the effects of lunar dust on equipment.
Yeah, so the simulant has similar composition and particle size distribution. Is that
Exactly.
Is that correct?
Yep, and depending on the type of test you're doing, sometimes you might care more about particle size distribution and the angularity. If you were doing an abrasion study to see how this material abraded fabrics, for instance, then you would want to use a simulant with those characteristics. If you were doing something more like trying to extract resources from the simulant, then you'd want something that's more chemically representative.
Interesting. So you could order a simulant with different properties depending on what you really want to use it for.
Yep, exactly, and that's what hardware owners do. Folks that are building hardware to go to the surface of the moon, whether that's payloads or landers, even to study the impacts to crew health. There's a whole different collection of simulants they can choose from.
And now, in terms of corrosiveness to mechanical things like axles and bearings and seals, I'm thinking this stuff is going to be pretty hard on physical mechanisms.
Yep, absolutely. So that's actually a huge area of research, is what we call dust-tolerant mechanisms or dust-tolerant components. And so really anything that will be interacting with the surface, so wheels on a rover, any sort of mechanism, even the hatch door that opens and closes at the end of an EVA, even the docking mechanism that docks to another vehicle, all of those things could be affected by dust. Sometimes even just a small degree of dust can affect the performance of a system, and sometimes it takes a little bit more.
What about fabrics, like what we have the spacesuits made out of? If you get this working into the fibers of the fabric, I'm thinking that it could cause abrasion and maybe even weakening of the fabric material itself.
Yep, absolutely. In fact, I have a spacesuit glove right here, so we'll try not to get lunar simulant on this, but the outer layer of the spacesuit, actually that material could be susceptible to lunar dust, and so you have to make sure that that the dust doesn't get into your spacesuit, because like you said, it could abrade the the fabric itself and then get into the weave of the fabric. So that's obviously a problem for the spacesuit. And then it's also a problem when the spacesuit then comes back inside the pressurized volume. This is the biggest way that dust is going to come inside.
So what kinds of methods do we have to get the regolith off of your spacesuit before you come back in? You've done a spacewalk, you've been outside for 8 hours, you're dead dog tired, you're ready to get back inside, and you're all dirty, and you need to clean your suit off before you come inside. How are we going to do that?
So we actually have a few different methods. We look at passive mitigation and active mitigation. Passive basically meaning there's no human in the loop or no power in the loop, depending on the situation, and active meaning you either have power or human in the loop. So a couple fun examples for active mitigation, we have something called the electrodynamic dust shield, which takes advantage of the charged particles, right, the positive and negative charges of the lunar dust, and basically, it helps, you basically have a charge on your surface, whatever your surface is, whether it was on a solar panel or even on fabric, and you can actually bounce the dust off of your surface. So that's called electrodynamic dust shield, or EDS. But there's other techniques like compressed gas, using any sort of compressed gas. If you could take advantage of some of the consumables maybe and use that to actually blow the dust off of your surface or system. There's things using electron beams and ionization to remove dust as well.
It's too bad we can't use a vacuum cleaner while we're outside on the moon.
Yeah, that would be tough in the vacuum of space, but inside a pressurized volume, you can use vacuums.
Yeah,
So,
for sure,
Yep.
for sure.
So
You
that's
could use
part
a
of the plan.
vacuum cleaner. Now, so you've cleaned up your suit, you're inside, hopefully you have some kind of an airlock where you can leave all the dirty stuff in the airlock, and then the crew can maybe change their clothes or whatever, and then they can be in the crew module part of the lunar lander, and you can keep that clean. I'm thinking that in 16G, which is lunar gravity, that the dust will not be as inclined to settle as quickly, especially the find.
Absolutely, yeah. So we can look at pictures and videos from Apollo to see kind of the ballistic trajectory of, say, a wheel going through the lunar dust to see how the simulant or the dust in that case actually falls. But you're right, inside a pressurized volume, it takes a while for the dust to settle. And then as you're ascending, so your vehicle that you've brought dust back into is eventually going to ascend to get back into orbit. And then you would expect, particles to be lifted up again.
Oh, well, and during the ascent phase, the particles will all get pushed down to the direction of the G vector, but as soon as you have engine cutoff, everything's gonna come floating back up.
Yeah, exactly. So we have to work very closely with different system and subsystem owners. So the folks that work on filtration and the environmental control systems inside of the habitats or pressurized volumes, we work closely with them because we have to time these things just right to make sure when something like that happens during engine cutoff that we're able to scrub the air of the dust.
Now, what about dust sticking to the outside of the spacecraft, maybe making it up through ascent, and now you're getting ready to dock to Gateway, and it's this clean, pristine thing, and here comes a spacecraft equivalent of Pigpen coming up to dock, and they've got solar panels and radiators, and they'll probably even have observation equipment with lenses and mirrors and things like that they want to keep clean, docking back to space, to Gateway.
Yeah, that's a great visual. So yeah, the human landing system or HLS or any other vehicle that comes off the surface could exactly do that, be this Pigpen that then docks with Gateway, which is kind of like our space station orbiting around the moon. So we work closely with the Gateway program, with all the different programs that are going to be on or near the surface of the moon in that cislunar space to make sure that we're not bringing dust there. So there are theories and there's some modeling developments going on now to try to understand this better, that when HLS docks with Gateway, that there could be some transfer through electrostatics and other means of some of this Pigpen mess over to Gateway, both externally and then of course internally with dust going back and forth.
So we're talking about dust and how it builds up on other surfaces. What do we need to consider for some of our lunar surface assets?
Yes, that dust is everywhere, and one of the things we learned from the Apollo anecdotes is that the lunar rovers would kick up dust when they're driving around.
Does it affect any of the functions of it? I mean, we talked about the bearings and the
Yes,
wheels
yes,
and how
yes.
the dust will kind of grind it to pieces.
Yeah, not just those. That was a unique case, and even driving around was kind of unique because your rooster tail's at the back and you're not
Yeah.
stuff. But dust moves around
Sure.
either way, and it settles. It will float in the lunar surface environment for a very little bit of time. It's always on a ballistic type trajectory. What
Okay.
goes up comes down. Gravity.
Okay, gravity.
No wind resistance. Type of stuff. But the batteries on the front of the lunar rovers had to reject heat, so they had radiator plates on the top of them that were actually covered with dust covers, just fabric dust covers,
Right.
like the material from the spacesuit, I believe. And every time they would stop, they'd open them up and let the heat radiate into space
Okay.
through these radiators. But they'd also take a look at them, and they had this horsehair type brush, and they would brush them off.
Okay.
And they're looking through their helmet to this surface, brushing it off, and they look at it and it's clean, and they go put the brush away and go about their business.
Right.
Well, a couple of times, or at least one significant time, the battery started overheating.
Oh.
But the dust acts as an insulator to a certain extent, but they couldn't see it. It was below 50 microns in size dust that you can't see with the naked eye. So they were just moving dust around these glass plates and not even noticing it because
Right,
it looked clean.
it was too small.
Yeah, and it looked clean. So
Sure.
So that was one of the lessons learned, that the smallest of the small dust could affect performance of certain hardware in unexpected ways, like
Right.
radiators or possibly even solar panels. So we have to understand how that works and prepare for it.
Okay, so like the poles on the Earth,
Yeah.
the south pole of the moon is different than the equator of the
Yes,
moon where our
yes.
Apollo astronauts
Yes.
visited.
You get sun higher in the sky and you get sun lower in the sky.
Okay.
The Arctic Circle on Earth, if you go up to Alaska, there are certain points in the fall and in the spring where the sun is right around the horizon, either right below or right above.
Sure.
In the summertime, it never gets below the horizon, but it doesn't get very high in the sky. In the wintertime, it gets below the horizon, and it's always nighttime. We recently visited one of the JSC lighting labs. We'd like to show you that information next for the lighting conditions on the lunar surface.
I'd like to see that. Thanks.
Hi, I'm Ben Green, Deputy Manager for EVA Development here at NASA. I'm joined by astronaut Jessica Meir. Jessica, it's great to be with you. So we're here today at the lighting lab at the Johnson Space Center. This is where we simulate lighting conditions in space and on the lunar surface. This is where we evaluate lots of different hardware, like the new spacesuit that the crew will be wearing, or one very similar to it when they go back to the moon. As you know, when we go back to the moon, we're not going back to the same locations that we explored on Apollo. We're going to the South Pole. And at the South Pole, the lighting and thermal conditions are very different than
Right.
around where we went for Apollo. On the South Pole, the sun rarely peaks above the horizon or just below the horizon. So because of that, a lot of the surface of the moon actually never sees the sun. There are parts of the moon in craters that have not seen the sun in over 1 billion years. And the areas that do see the sun only see them for moments. The shadows on the lunar surface are very long. There are mountains in the South Pole that the shadows are upwards of 75 miles long. So all the rocks and all the features on the lunar surface cast these very long shadows. And so why is that important to us? Why do we care? Well, we're going to the South Pole because we want to explore those areas and look for different geology features, rocks, ice, if we could find it. I mean, if we could get down into a crater that's been dark for 1 billion years, there might actually be ice there, and that would be super exciting if we could find that.
And that's one of the interesting scientific points, right? In these permanently shadowed regions, as they call them, that are always in the shade, there might be the presence of these volatiles. Actually, we know there
Absolutely.
are volatiles there, right? What does that really mean? Why are we interested in the volatiles?
So if we can find those volatiles, there are lots of things that we can do with those. So ice could help us generate oxygen, potentially fuel, and help us establish a base on the South Pole that we could go to Mars or lots of other different areas around the solar system, a launching off point, if you will.
And with humans there, we could potentially even drink that water, right? If we're able
Absolutely.
to extract that from those volatiles.
Absolutely.
I had the opportunity of being in one of the lighting simulations that we had over in Building 16, where I drove the rover and then also did the VR spacewalk with those lighting conditions. And I was really surprised by how challenging it was. I mean, there were times when I was only had the lights of the spacesuit and I didn't have the rover. So we were simulating that the rover had failed and I didn't have that extra lighting. And so there I was, and I had to get back to the habitat, and I actually had to bend down sometimes because I didn't even have enough light to see the ground in front of me and make sure that I was walking safely.
When you're walking around in those very dark regions, safety is very important. The last thing we want you to do is trip over something that might be behind a rock or in one of those shadows, right? So you absolutely need to be able to see where you're walking as you're exploring.
You can see that here a little bit, like how these shadows, even just from the lighting setup that we have here, if I were walking across here, it would really be pretty difficult to see what the terrain is, see how steep that is to go down into that crater.
Yep, absolutely. So we want to provide some kind of supplemental lighting. So as you can see on this demonstration unit of the government version of the spacesuit, there are lights above the helmet here, and we have a camera mocked up there. So those lights are stationary, right? And so just like you said, they're shining out in front of us. They don't necessarily illuminate your feet perfectly. I mean, you can bend down and get a little bit of better illumination. And we've actually evaluated how well lights like these light up the ground in front of you, and they do a pretty good job. We'll also be supplying you with handheld flashlights.
Okay.
Also though, because a lot of this surface has never seen the sun or doesn't see the sun very often, it's very cold. Mm-hmm. So if you fall on your knees or even on your hands, that regolith is very cold. It's not very conductive, but it can still pull the heat out of your suit, and we really don't want that to happen. Around the South Pole, the main thing we're worried about is getting too cold.
Because the temperatures can be really extreme on the moon, right? Like, isn't it something like from 250 Fahrenheit to negative 210-ish or something like that, depending on if you're
actually below 300 Fahrenheit.
Okay, even on the poles, it's even more than that.
Yes.
Okay.
Where we're going, that's right.
So how does that compare to, so for example, I was fortunate enough to do 3 spacewalks on the space station. How does that compare to the thermal extremes that we saw out there? And what's the difference? You mentioned the conductivity of the regolith. Like, what are the differences there?
So the way we deal with the cold extremes on the lunar surface, the suit is made up of this, what we call multi-layer insulation. And so it's layers of aluminized mylar and then other materials in between these aluminized mylar.
So that's
to
all in
create a
here.
thermal barrier. That's right. That's
Okay.
all on this outside surface and this white material that's on the spacesuit back here. And so this is how we keep you warm in this extremely cold environment. And it's a passive system, like I said. We don't have any active heaters. That takes a lot of power, and we don't have a lot of room for a lot of batteries. And so that'll limit the time you have outside. If we're spending a lot of that energy heating you up, then you don't get to stay out.
But there's a cooling system, just not heat?
There is also a cooling system that you wear, but there is no heat.
Okay. So that's going to be one of the big challenges for all the equipment we're using, right? Is this regolith and this dust that kind of can get everywhere. If you have, I imagine, any kind of thermal control system with a radiator or something to dump heat, how are we coming up with new technologies for that, or what's kind of been done in that area?
That's a great question. So we are actually doing technology development projects that are looking at sensors for telling us when we've got a lot of dust accumulating on surfaces like radiators, solar panels. And if we could have a sensor that tells us, hey, we're starting to accumulate too much dust, that we've got to go out there and actually go and sweep it off. Or some of that might tell us that, hey, maybe we need an automated way of, like windshield wipers or something, to wipe off all that dust. Because just a small amount of dust can change the optical properties and start really hampering the efficiency of our ability to reject heat on our radiators.
Are there different materials that we can use that maybe would be able to reject some of that dust somehow, or prevent it from adhering, that kind of thing?
So we are looking into that. So we are doing other technology development to look at materials that don't capture the dust. The fine dust on the outside of the suit as much. There's other issues though that we're working with. So not only does the dust get mechanically trapped in the outside of the suit, it gets bound electrostatically. So as we walk around in that dust on the lunar surface, we're building up a charge like you do, like when you walk around in your house with your socks on carpet. If you still have carpet, you'll develop a shock and you'll touch somebody and a spark will happen, right? So a similar thing happens on the lunar surface, and that'll cause the light dust to stick to the outside of the suit. So we are developing a neat little anti-electrostatic gun that we're testing right now in relevant conditions to get rid of the charge and help the dust just fall off of the suit.
I imagine that could damage equipment too if you're building up that electrostatic potential.
It can. So we have to deal with that as well and try to figure out ways to eliminate the charge built up on the suit, because that is another concern. If we have a charge on the suit and come back to the vehicle, we could touch the vehicle, and that same kind of spark that you get walking around in socks, we don't want that happening on the suit, because that could also damage the suit.
So you mentioned that the space station suit has a requirement for 250 to minus 250 Fahrenheit. So what's the requirement? Is that different than, since we know going to these areas that might get colder, do we still have a temperature limit so we know, we can't go in this one area? Or?
So interestingly enough, on the cold side, there isn't really a limit. There is a temperature at which the amount of heat that we're leaking out of the suit starts to level off to where the colder we get, it's actually not a problem. So in those super cold regions, like I said, though, it's more how we're walking around. Our boots get colder than our upper torso, right? And so because our boots are in that super cold regolith, we're leaking heat out as we're walking around. And so we're limited from that perspective. In fact, we've got a boot here. And so the way we're dealing with that cold regolith is through a passive insulative layer on the bottom of the
so it's nice
sole.
and thick. This looks a little bit like what we call bunny boots. I did my PhD work in the Antarctic, and we had these big white boots with a really, really thick sole like that. And that's what, when we're walking around in the Antarctic on that sea ice where I was working with penguins, in order to stay warm, it's always the feet and the hands that get cold first. So
that's
it's kind of similar to that.
Right. So the soles on the boots that we'll walk around on the South Pole will be very thick, just like you said, and there will be insulative material in here to prevent the heat from leaking out into the ground and keeping your feet warm.
Fascinating.
Yeah.
Thank you. Thank you,
Certainly.
Don, very much for this discussion
pleasure.
today.
It was
It's been a
great.
great episode. Thank you for sharing with us
Anytime.
some of the
Anytime.
lunar challenges.
Yep, lots of them. We'll work on them.
That's right.